All right, we have now completed a good chunk of the kinetics that we're going to talk about this year, this semester. We've talked about all the basics, and we've also talked about all the stuff to do with mechanisms and elementary reactions and that kind of stuff. One major topic remains, well, one major topic in kinetics proper, in the sort of kinetics background, as opposed to enzyme kinetics, which is coming up next. That topic is rate constant theory. We want to understand what it is that goes into a rate constant. Now let me say at the outset here that there is no really good predictive theory for rate constants. There are qualitative theories, and that's what we're going to talk about. But really good predictive ones from first principles, that is, where you start with the molecule and then you calculate the molecules that are involved in the reaction, and then you calculate the rate constant for that reaction, is extremely difficult, even with the fastest computers, even with the best theory available today. So rate constants are still an area of active research. It's not a real hot area because there's not much progress being made. It's a really difficult problem. And what that means for us is that we're going to look at just some of the simpler qualitative theories. In particular, we're going to look at Arrhenius theory. I think probably everybody has seen that before. Then we're going to look at Eyring theory, transition state theory. There is a simple version of Eyring theory, and that's mostly what we'll talk about. And that simple version of Eyring theory is very similar to Arrhenius. So really, we're going to talk about all these guys at once, together. We'll talk about Arrhenius and Eyring together because they do overlap quite a lot. However, there is a more complicated version of Eyring theory, and that's what I really mean here when I'm talking about transition state theory. That involves a lot of stat mech. It's very powerful. It allows you to understand in some considerable detail what controls the rate constants for reactions, for very simple reactions with simple molecules, very simple molecules. However, we won't have time to go into that in great detail. In other classes like the two-semester Chem 311, 312, we have more time, and then I do go into this, and we can do complex calculations. And it's very illuminating and very helpful, but we just don't have time for that in a one-semester Chem class. I will make allusions to it, but we won't go through it in detail, even though we have at least some of the background for it. All right. There are other theories as well. There's something called Cramer's theory, very powerful. I've used that a lot in my own research. And then there's just a ton of others. Because this is an area of active research and there is no, sort of dominant preferred theory by everybody, there's just a lot of other theories. But these get increasingly complicated as we get away from Eyring theory and Arrhenius theory up here. And so we won't talk about any of these. Cramer's theory in particular depends on diffusion theory, which we also did not cover this semester, though I think it's in chapter 17, and so if you look at diffusion theory there, you'll at least get a little bit of an introduction to the ideas behind Cramer's theory. All right. Let's talk then about the key ideas behind all of these theories. One of the key ideas is this. First of all, we're going to talk about rate constants just for elementary reactions. These are not the rate constants for complex reactions that have intermediates and the like. These are only for elementary reactions. And for an elementary reaction, a single elementary reaction, it very often happens that you have the reactants, you've got the products over here, and then there's something called a reaction coordinate, and I can give you examples of what that means in specific cases, but basically it's a variable or a degree of freedom in the full system. If there's several molecules, it's something to do with all the molecules as a collective thing, not any one molecule. And we won't go into it in detail, but it allows you to put the progress of the reaction along one axis. In other words, as we move from this side to this side, we're moving from reactants towards products. There's a lot to say about this, and again, in other classes, I would say a lot more, but suffice it to say that the key idea is that as you're moving along from reactants towards products, generally the energy has to go up. There's something in the middle between the reactants and products called the transition state. You will recognize that term, right? It was up here already, transition state theory. Transition state theory, as the name implies, uses the idea of a transition state as sort of a middle point between the reactants and the products in order to do a lot of calculations and come to some understanding of how the whole rate constant behaves, how the rates of reaction are controlled. Well, the key idea here, though, is that because the energy has to go up, there's a barrier between the reactants and products. In order to go from reactants to products, you've got to suck energy in from the surroundings, and we all know that that's entropically disfavorable, right? And because it's entropically unfavorable, it doesn't happen very often. There's a low probability of doing that. And that's the reason why reactions take so long. If there were no barrier, if the diagram looked like this, so you could go from the reactants to the products without any barrier, the reactions would be very quick, and so quick, in fact, that you could hardly follow them. You'd need a laser and a pulsed laser and picosecond time resolution or faster in order to even follow them. The thing that slows reactions down is that kinetic barrier. And that means that this kinetic barrier has to be a certain sort of minimum height, or else the reactions just get very fast, and we don't normally even pay attention to such fast reactions. So all the barriers we're going to be talking about are pretty high, and we'll talk about how high that is in just a second. All right. So what I just talked about is another one of the key ideas. The reactants are at relatively low energy. They may not be as low as the products. In fact, oftentimes the energy doesn't have to go down when you're going from reactants to products. It can actually go up. The curve can look like this, right? You can have the products at higher energy than the reactants were, but it usually goes down for a spontaneous reaction anyway. But it's lower here at the reactant side than it is up here at the transition state, and also lower on the product side than it is at the transition state. The transition state is the highest point anywhere on the diagram. And so the products are also at low energy relative to the transition state, but the transition state is at high energy, and therefore, yes, there's a kinetic barrier between the reactants and products. And yes, that means you have to put energy in from the surroundings. And that means that you can think of the reactants as sort of sitting and along this part of the diagram and jittering back and forth or fluctuating back and forth, running around in here due to thermal energy. And some of those movements, the movements that take you in the correct direction towards the transition state over here, can be thought of as an attempt to go over to the products over here. And that attempt has a certain probability, which depends on how high this barrier is, and a certain rate. A certain number of attempts are tried per second. And so the success probability is one of the key ideas. The success probability is usually very low because the barrier is quite high. We'll see. Typical barrier is, in fact, around 50 kilojoules per mole. The available thermal energy in the background at 300 Kelvin anyway is about 2.5 kilojoules per mole, which means that we need to get enough energy to be 20 times bigger than the usual available energy, RT. And that means that the probability of getting up all the way up to the top here is typically proportional to a Boltzmann factor, e to the minus e over RT, and that's about e to the minus 20 for a barrier this big and at 300 Kelvin. So there's a big unfavorable probability factor that makes it very likely. I mean, most of the attempts are going to stop down here, right? They're going to get a little bit of energy, and then they're going to fall back. It's only when you get one of these really rare ones that gets you all the way up to the top that you can actually continue on and go to products. And so one of the key things that controls the rate of reaction is how high this barrier is, and therefore what the probability of success in reaching the top of that barrier will be. Another key idea is that there's a certain maximum attempt rate, even for the very fastest reactions. And this quantity comes from Eyring theory. I say it here, in fact, I don't need to spell it out. And where that number comes from, I don't think we'll talk about, because that would involve deriving Eyring theory, and I don't think we want to spend the time to do that, especially since the derivation is quite a few steps and a little bit of pretty subtle logic. But this is KBT, the normal thing, so it's kilojoules per, well, it's 2.5 kilojoules per mole at room temperature. And this is Planck's constant. So we haven't talked about quantum mechanics in this class, and we never will talk about quantum mechanics in this class, again, for lack of time. But Planck's constant is a marker for quantum mechanics. If you see any formulas and it's got this H in it, then quantum mechanics was involved at some point along the route. And that's telling you that Eyring theory used some quantum mechanics along the way, because that H is in there. Well, one of the conclusions from Eyring theory is that KBT over H, which has units of 1 over seconds, or seconds to the minus 1, is the very fastest possible reaction rate. If we put numbers into that, the KBT in joules, so microscopic units, is 4.1 times 10 to the minus 21 at room temperature. And then H, Planck's constant, is 6.626 times 10 to the minus 34 joule seconds. So this is joules up here and joule seconds down here. And that gives a value of 6.25 times 10 to the 12th seconds to the minus 1. So keep that number in mind. It's a good benchmark number. It tells you what the very fastest rate constants can be. It is very fast. If you have a reaction that's got a rate constant anywhere in the vicinity of that rate, then it's going to be just really too fast to even follow. It says that this is the maximum attempt rate. Remember the maximum attempt rate that we have at the bottom of the hill here. And that happens, the attempts occur, therefore, at a rate of about 1 every 10th of a picosecond. So very short, very, very rapid attempt rates. These are basically vibrational rates. It's basically, if you've got a chemical reaction that's breaking a bond, the way those bonds break is by stretching their bonds, and that's a vibration. That's basically a molecular vibration, a big molecular vibration that actually breaks the bond instead of just being a little one. And bond vibrations happen typically on this time scale. So it's not surprising that this is the very fastest attempt rate and also the very fastest rate constant, because it's also basically got a physical foundation in the rates at which vibrations occur. All right, so the core idea then, or the core buildup that I'm building up to here, is that the rate constant should be the rate at which you make the attempts times the probability that any one of your attempts is successful. So it should be attempt rate times success probability. And that's exactly what both Arrhenius and Eyring formulas give us. So again, for elementary reactions, this diagram with only one bump only applies for an elementary reaction. If you've got something with more than one bump in it, which you can have in principle, then that's no longer an elementary reaction. But then you usually divide the system in half and you talk about one bump at a time. And as we've seen, talking about elementary reactions is good enough because you can always build up any other reaction from elementary reactions. So if you've got a theory for elementary rate constants, that's a theory for everything when you get done working everything out. All right, so for elementary reactions, the Arrhenius law, and again, I think most people have probably seen this, says that the rate constant is equal to a quantity A, which is called the pre-exponential factor, and that's our attempt rate, right, times a probability factor, which is basically a Boltzmann factor, as you can see, e to the minus activation energy, EA, divided by thermal energy, RT. So this is the success probability, this is the attempt rate. The I-ring theory, on the other hand, is a little bit more complicated because it's based a little bit more on ideas of molecular structure, and so the I-ring theory says the following, that the rate constant is equal to kBT over H. Notice that's the same quantity that we calculated up here. That's from I-ring theory. There's an extra little C0 in there. We'll talk about that in a minute. That's basically just a units fudge factor. Times e to the minus an energy over RT, but it's a free energy. It's a Gibbs free energy. It's the free energy, that change that takes place when you go from the reactants down here up to the transition state. So delta G double dagger is the free energy change, not to get all the way over to the products, but just to get up to the top of the hill, to the transition state. And so all these, we're going to see a bunch of quantities now with this little double dagger symbol. That double dagger symbol is the marker for a quantity that's associated with the transition state. So that looks a little bit like the Arrhenius form already, right? It's got a pre-factor and then it's got e to the energy over RT. But remember that the Gibbs free energy is delta H minus T delta S. It's got a delta H term, and that really is like energy, but it's also got an entropy term, T delta S. And if we substitute that in there and then do a little bit of, well, one step of algebra, we can rearrange this I-ring formula to this form. Let me put it this way. Let me circle it this way. And now it really is closer to the Arrhenius form. So if we assume that this delta H is pretty close to the energy of activation, and in fact, in this class, we're going to say that they're the same. They aren't really quite the same there. And in some special cases, there's a significant difference between the two. But for our purposes, we don't need to worry about that. So we're going to say that they're the same. If that's true, then this has to be A, right? This has to be the attempt frequency. But you can see it's got this kBT over H. That's the maximum possible attempt frequency, multiplied by a term that depends on the entropy change when you go from the reactants up to the top of the barrier. So when you go up to the top of the barrier, now there's a delta G, but there's also a delta H, and there's also a delta S. When you go from the reactants here up to the top of the barrier. Now, so far I haven't said anything about what's really going on at this transition state. I'm now ascribing properties that won't make any sense until I start saying something about what's at the top of the barrier, but we'll do that next time. We won't have time for that today, I don't think. A lot can be said about what's going on at the top of this barrier here and what the molecules actually look like when they're at the top of the barrier. And then these quantities delta H and delta S and delta G start to make more physical sense, more sense in terms of the molecular structure and so on. But we'll come to that. That's not for yet. All right, so this is the I-ring formula then. You can see that it's very close in spirit, especially, to the Arrhenius formula. The Arrhenius formula is obviously a lot simpler. And let's look first at what's in here. We've already looked at the kBT over H, right? That's the Planck's constant. There it is, 6.626 times 10 to the minus 34. There's this C0, which is the units factor. We'll come back to that. There's this delta S, which is the entropy change to reach the top of the barrier. And there's this delta H, which is basically the same thing as the energy of activation. It's the enthalpy change needed to reach the top of the barrier. All right. Yes. So here I'm saying some of the things I said before. The barrier is now thought of as a free energy barrier, not a plain old energy of activation barrier. And there's an energy, therefore a free energy, an enthalpy, and also an entropy. And again, yes, we'll come to talk about all those things later. Now, there is a subtlety, and that brings us finally to this C0 that I've been referring to all along. And that is that if you're looking at a first-order reaction, then K has to have units of seconds to the minus 1, right? But if you're looking at a second-order reaction, then K has different units, molar to the minus 1, seconds to the minus 1, which means that this A isn't the same thing depending on whether you're talking about a first order or second order reaction. Its units have to change. That means also its physical nature is changing. That's all right. That just means when we talk about A values, we have to be careful to choose the units for A, and when we're doing calculations to see that we're getting the right units for A so that they match the units on the rate constant itself. That's because this part, right, doesn't have any units. This exponential is unitless. So the units on K and A have to match each other. Usually that works out rather naturally. It's usually you're calculating A from data that you've got on K, and then K is involved in the calculations naturally, and it normally just works out obviously that A has the same units as K. On the other hand, down here for the Eyring formula, again, we've got the same issue, seconds to the minus 1 for a first order rate constant, molar to the minus 1, seconds to the minus 1 for a second order rate constant. But kT over H, as we saw above, is joules over joule seconds, which always has units of 1 over seconds, or seconds to the minus 1. So kT over H by itself always has the units as if we were talking about a first order rate constant. We want to be able to talk about second order rate constants, though. And it turns out that if you go through all the derivations, what happens in the second order case is just that you get an extra concentration unit. And we're free to choose our units of concentrations and our standard state for concentration. And so we choose C0 to be 1 molar, which makes the units on this whole quantity out front match for a second order rate constant. And I guess the only other thing to say is that what that means is that this C0 really isn't there for the first order case, or you can take it to just be a 1 without units for the first order case. And it is there with full units, 1 molar in the second order case. All right, let's do an example then. Let's consider, first of all, we're at 300 Kelvin as is sort of the default temperature. We're going to consider an elementary second order reaction. A plus B goes to C. We collect some data and we find out that the rate constant for this second order reaction is 10 to the minus 2 molar to the minus 1 seconds to the minus 1 when the temperature is at 300 Kelvin. But if we raise the temperature to 310, then it's 3 times bigger, 3 times 10 to the minus 2. And that's enough information, it turns out, to find the energy of activation and the pre-exponential factor, and also to predict what the rate constant will be at a higher temperature, so at 350 K here. All right, now let me say, I'll say it again down later. The Arrhenius theory, well, where are we? Here we are, wasn't derived from first principles. It's really a very phenomenological theory. That is, it's something that works. But there's always a question whenever you have a new reaction, whether or not the Arrhenius theory is valid for that reaction or not, because it's not based on first principles. The Eyring theory is much more based on first principles. It has approximations and stuff, but it has a long derivation from first principles too. And so the Eyring theory is much better founded. And in a lot of ways, Eyring theory is used to justify Arrhenius theory up here, which was just sort of postulated way back in 1900 or so, a long time ago, by Arrhenius, who was a very incredibly smart guy back in the turn of the century. Anyway, that means that we have to be a little careful when we're applying Arrhenius theory, and here we are going to be applying Arrhenius theory, right? We're asking for Arrhenius parameters, E, A, and A. Those come from the Arrhenius theory. Those are not Eyring theory. And then we're asking for a prediction that's rather far from the temperatures that we started with, right? We start at 300 K, now we're going to 350 K. That's about the limit over which you can really trust Arrhenius theory. If we tried to go to 400 K, for example, probably Arrhenius theory is not good over that big of a temperature range. So I sort of picked a big range here so we'll get a dramatic result, a big change. But a warning that you have to be a little careful with Arrhenius theory sometimes. We'll talk about Arrhenius plots down below, and that's a way to test whether Arrhenius theory works or not. If you get a straight line in an Arrhenius plot, then Arrhenius theory is good, and you can use it. If you start getting curved lines, then something has gone wrong. All right, the theory has failed. All right, so to answer these questions, first of all, this is what we have, right? Suppose I take this formula at two different temperatures. So I take K2 at temperature T2, and I divide it by K1. Oops, that should be a 1. At temperature T1. Then the pre-exponential factors don't depend on temperature, so they divide out. And if doing a step or two of algebra, you get that K2 over K1 is equal to e to the minus energy of activation over R times 1 over T2 minus 1 over T1. That should look familiar, except for the fact that this is an EA and these are rate constants. It's the same as the Van 't Hoff theory that we looked at earlier. Here's the Van 't Hoff formula. These are equilibrium constants, not rate constants, and that's a delta H, an enthalpy, not an energy of activation. But mathematically, except for the names and the physical interpretations, mathematically it's the same thing. It's the same equation from a pure math point of view. So that means this relationship should be familiar. Everything we said about Van 't Hoff applies to this Arrhenius equation version 2. So this allows us to relate a change in rate constant with changes in temperature to the activation energy. Let's see how that works. So we take the natural log of both sides, here and here. Then we rearrange to solve for EA, and we get that the energy of activation is equal to minus R log of K2 over K1 divided by 1 over T2 minus 1 over T1. That should look familiar too, right? We did a lot of problems like this for enthalpy of reaction minus R log big K2 over big K1. Those are equilibrium constants, 1 over T2 minus 1 over T1. So again, everything we learned about Van 't Hoff we can carry right over to Arrhenius too. All right, now we just have to plug in numbers. EA is equal to minus 8.314 log 3 over the two temperatures. And if we do the arithmetic, that gives us 84.9 kilojoules per mole. I said earlier that a typical barrier height is about 50 kilojoules per mole, so this is on the high side. But even higher barriers are not unknown. 100 kilojoules per mole, even higher than that, do occur fairly regularly. So this is within the envelope of typical, it's on the high side, but it's within the envelope of typical barrier heights. All right, yes, this is a good point to make at this point. Notice that the energy of activation we got is positive because of the way the energy of activation is defined, right? It's the barrier height, and it's the difference between the reactants and the transition state, it's always got to be positive. The barrier has to be higher than the energy of the transition state. So energy of activation is always a plus number. If you get a negative number for any energy of activation, you did something wrong someplace. And another consequence of that is that it means that the rate constant must always increase with temperature. Remember that the equilibrium constant doesn't always increase with temperature. If the delta H of reaction is greater than 0, that is for an endothermic reaction, then the equilibrium constant increases with temperature. But if you have a delta H that's negative, an exothermic reaction, right, then the equilibrium constant actually decreases with temperature. But you can't have a negative EA. EA is always greater than 0, which means that following the same logic we used for Van 't Hoff, the equilibrium constant the rate constant always increases with temperature. So rate constants behave differently than equilibrium constants. All right, now the problem also asks for our pre-exponential factor here. We can get that by just solving for the pre-exponential factor at any one temperature, right? This is K is equal to A e to the minus EA over RT. Solving for A here. Notice the units matching, right? K, oops, that's the wrong value. I changed these values and forgot to change it here. K has the right units that are going to give units for A. So this is just like I was saying. If you use the right units for K, you're going to get the right units for A. We divide by this exponential factor. We now know what EA is. If we plug the numbers in, here they are, then you get an A of 6 times 10 to the 12th. In other words, this A is close to the maximum possible rate at which it can go. So this is a high enough barrier so that we get a pretty slow rate even when the pre-exponential factor is as big as it can possibly be. Now, last part of the problem says we want to predict the temperature at 350 K. So all we have to do is plug in, and with the numbers that we now have A and EA. We put in 350 there, and there's the arithmetic, and we get 1.3 molar to the minus 1 seconds to the minus 1. That still doesn't look very big, but remember that the original at 300 K, it was 10 to the minus 2 molar to the minus 1 seconds to the minus 1. And so it's gone up by a factor of about 130 over the course of our 50-degree change. And that's not remember I said earlier when we were talking about Van 't Hoff that there's a rule of thumb, which is that if you change the temperature by 10 degrees, you can expect a doubling. And that applies here too, because the math is the same. So you change the temperature by 10 degrees, you can expect the rate to double. That's only true if the barrier height is 50 kilojoules per mole. That rule of thumb applies to the sort of most common barrier height of around 50 kilojoules per mole. And so it doesn't obviously apply when the barrier height's quite a bit bigger in this case. So we're going to more than double for every 10 degrees that we go up. Well, we've gone up 5 times 10 degrees, right? We've gone up 10 and 10 and 10 and 10 and then another 10. And so it's not surprising, and we're more than doubling every time. So it's not surprising that we have a big change in the rate constant. And so one of the lessons from this little example is that rate constants can change a lot with relatively modest changes in temperature. A 50-degree change is not any huge change in temperature, and yet it has caused, it's caused a chemical reaction that might not be going at any appreciable rate at all at room temperature to suddenly be quite fast. All right. One more thing, I think, before we quit. I think that's the end of the notes anyway. So let's talk about Arrhenius plots. There are Van 't Hoff plots, right? And the math is all the same, so we should expect to have Arrhenius plots too, and I mentioned them up above anyway. If K is equal to A e to the minus EA over RT, we could take the log of both sides and then rearrange that to get a form that tells us what sort of thing we should plot to get a straight line. If we plot the logarithm of k versus 1 over t on the x-axis, then according to this mapping, we should get a straight line, and that's an Arrhenius plot. So log of the rate constant divided by 1 over t should give us a straight line, and the slope of that straight line should be minus the activation energy over r. So we can get the activation energy by taking the slope of an experimental bunch of data where we've measured the rate constant as a function of temperature. The intercept out here is also the logarithm of the pre-exponential factor, though intercepts like this are prone to large errors, because if there's any error in the slope here, then the intercept starts moving a lot on this y-axis, so that's not as useful a number in general. Let's see, there was something else I wanted to say. Oh yeah, and of course all this should again look familiar. It's the same as a Van 't Hoff plot. Change this to log of the equilibrium constant, and it is a Van 't Hoff plot. So everything we said and did with Van 't Hoff plots earlier, we're going to be able to carry right over to Arrhenius plots. Yes, the energy of activation must be positive, which means that the slope's always going to go down. For a Van 't Hoff plot, the slope can go either up or down, because delta H can be either positive or negative, but EA has to be positive, so the slope's always going to be down. Yes, final comment. If you have a big energy of activation, as we saw up here in this example, in fact, where we had a pretty big energy of activation, then you can see in this formula that that's going to make the rate constant more sensitive to changes in temperature. There's a big number here. Now small changes in T are going to cause big, because it's up in an exponential after all, going to cause big changes in the K over here. And so when you have a high barrier, a big EA, then you have a low success probability and probably a slow rate. But you also have rapid changes with temperature, so that means the reaction, even if it's slow at room temperature or whatever temperature you start at, it can be sped up, if you want to speed it up, a lot by relatively modest changes in temperature. On the other hand, if the energy of activation is small, then the opposite is all true. You now have a high success probability. You don't have much of a barrier to get over anymore. You can get over the barrier easy, but the rate constant is much less sensitive to temperature. Sometimes that's good, sometimes that's bad. It depends on what you want to do. Yeah, and okay, that is it for today.